When designing an unbalanced distribution network, you have the option to choose between DYN1 or DYN11 vector groups for transformers. This option allows you to investigate the impact of transformer winding connections on voltage angles, which can be important to understand before connecting two or more transformers in parallel. Xendi leverages OpenDSS's multi-terminal design paradigm and exposes control over winding connections through the decomposition of a typical three-phase two-winding transformer object into separate single-phase transformers that are externally interconnected to yield the same results as a single three-phase unit, but with the added capability of vector group control. So rather than using a single three-phase two-winding transformer for our design, we will connect bus 2 and 3 together via three separate single-phase transformers. To do this, we will click on a transformer symbol shown here, and we will toggle off phases B and C in order to define this as a single transformer connected to phase A. By default, single-phase transformers are set up with YY windings, but we're going to change this in a few minutes. We will insert another transformer connecting bus 2 and 3 and will define it as a single-phase transformer connected to phase B. And finally, we will insert our third transformer and define it as a single-phase device connected to phase C. We will next connect our load to bus 3 via an overhead wire. Note that for this tutorial, I have defined the load and its connecting wire as three-phase. Now we will need to edit each of the three transformer models. First, we will set the secondary voltage to 240 or 0.24 kV, and we will choose a 167 kVA transformer from the built-in Xendi catalog. Now let's go ahead and change the primary winding to delta. Once we click Save, the network will be updated, and Xendi has built-in logic to eliminate voltage mismatches, so once one transformer's secondary voltage is set, the other three are automatically inheriting that value, and you're notified of this change as shown here. We will need to go ahead and define the other two transformers the same as our phase A transformer. Note that the winding types and voltage ratings on transformers in parallel must be identical, and ideally they should have the same impedance and tap settings. If you want to explore different tap settings or impedances for each phase, OpenDSS can handle it, and you can get really creative, but please be prepared to correctly interpret the simulation results. Once all three transformers have been modeled, we will now need to model our overhead wire, which will be a 4-wire three-phase configuration. We will define our phase wires as 1/0 AAC and the neutral as a number 6 AAC wire. And let's go ahead and place a circuit breaker on the 2 side of this connector. The last step is to provide the geometry data. We will assume the A and B phase wires are on a crossbar 8 feet apart, so X, 4, and -4, and they're connected to the pole at 25 feet above ground. Phase C will be placed at a height of 30 feet and connected to the center of the pole, so X, 0, and the neutral will be at the center too, but at a height of 20 feet. Okay, now that we have defined our overhead wire, let's take a quick look at the load. We have a 150 amp constant kVA load rated at 400 volts with a power factor of 85%. Let's save our network, and from the project annotation and settings dialog, we will define the transformer vector group to DYN1, which will configure the delta terminal connections so that the low voltage node bus 3 will be lagging the high voltage node bus 2 by 30 degrees. We will perform a power flow simulation via EPRI OpenDSS, and you will note from the back annotated simulation results that the voltage angle is not an option that can be viewed on the one-line diagram. This has been done to keep the user interface decluttered. However, detailed output results are available in Excel output files. And these are created with each simulation, and they can be downloaded to your PC for detailed investigation of the results. I'll go ahead and download and save the zipped output results for this simulation as dyn1.zip. Let's change the vector group to dyn11, which will configure the delta terminal connections so the low voltage bus will be leading the high voltage by 30 degrees. And again, let's perform a power flow simulation, and I will download and save the zipped output results as dyn11.zip. Now that we have downloaded our detailed output zip files, let's take a look at how assigning a vector group has impacted the behavior of the transformer connections. First, let's open up dyn1.zip and we'll examine voltages.cfv, which contains all the voltage values for our simulations. Note that our low voltage node bus, which is bus 3, is lagging the high voltage node bus 2 by 30 degrees for each phase. Since the actual OpenDSS script is also available to you from the zip file, you're free to edit your design in any way imaginable and directly perform additional simulations. Let's take a look at our output results for the dyn11 configuration and note how bus 3 is leading bus 2 by 30 degrees for each phase. Again, note that the actual OpenDSS script is included in the zip file with all the results. So you're free to edit and extend your design in any way you can imagine and directly perform simulations within OpenDSS. Well, this concludes our brief tutorial on transformer vector group modeling and analysis.